İyi günler. Burada olmaktan çok mutluyum. Bundan sonrasında İngilizce vereceğim konuşmanın. Thanks to everybody for coming here to listen for me reporting about some relatively recent research. So this is joint work with Pascual Restrepo, who's right now faculty at Boston University, and it's about robots and jobs. I think the sort of the broader topic doesn't need too much introduction. There is not a day that you don't read in newspapers about the implications of new technologies, the dangers, the promises of robots, AI, and but this has gone hand in hand with major changes in U.S. and OECD labor markets, and many people have expressed the concern that the negative trends that are quite clearly observable, and I'll show you some of them as we go along, in terms of employment, labor share, and relatively small growth rate of real wages over the last 30 years or so in the US, and similar trends in many other OECD countries are related to these to the implications of automation. And the question is not a new one, and many sort of major thinkers throughout the 20th century have expressed concerns about what machines will do to the labor market prospects of people. Keynes, for example, wrote in 1930, actually this was based on a lecture that he gave in the University of Cambridge in 1929, so before the Great Depression. He sort of wrote a very remarkable essay, essentially, about the prospects for our grandchildren, and he got many, many things right about how the economy and technology would evolve, including the steady productivity growth that we would be experiencing. But he also forecast that there will be increasing joblessness or technological unemployment, or much lower levels of employment for people. And he sort of coined the term technological unemployment in that context. Leontiev, writing about 2 decades later, sort of expressed similar sentiments in a slightly different context. He said, I cannot see how we can employ everybody who wants a job, and in fact he sort of mused that there wasn't any reason why people would not go the same way as horses. You know, at some point we thought we could not live without horses, and everything that the modern economy of the 19th and early 20th century did depended on horses, and then new technological improvements meant, you know, you had the rails, you had the trams, you had the internal combustion engine, and the horses became, you know, horse meat. So you know, those sort of sentiments were quite common, and then they did not come to pass. So this sort of frames a lot of the discussion in the current academic circles about these issues, that on the one hand, there are people who sort of worry about what these new technologies will spell out for labor, and they worry sometimes in rather alarmist terms. And on the other hand, at the other end of the scale, there are people who think, and that actually, by the way, includes the majority of the economists in major universities, especially in macro. You know, these things happened in the past. People worried about them. It all sort of worked out fine. There are strong forces for technological improvements to always translate into gains for workers, and there is no reason that this time will be different. And I think this dichotomy with alarmism at the one hand and sort of, you might want to call it complacency at the other end, I think is a false one. That not only the reality is somewhere in between, I think it's somewhere in between in a way that we don't fully understand. So that's what I want to talk about today. And I'm going to focus on industrial robots, but I want to also underscore that pretty much everything I will say conceptually is actually true much more broadly than than industrial robots. And what I'm going to do is actually I'm going to translate some conceptual framework that's based on some of my early work, but also apply them to the context of robots, where I will do much more detailed empirical work. So this, what you see here is just an example of automation, but it's a particularly telling example. This is a Hyundai factory, and the thing that's notable here is the absence of people. Essentially, every stage of the production process that was done manually by relatively skilled workers 30 years ago has been automated in this factory. And what I'm going to talk about are these robots. Of course, there are no hard and fast boundaries about what's a robot, but I'm going to follow the International Federation of Robotics, which defines an industrial robot as an automatically controlled, reprogrammable, and multi-purpose machine. Autonomous, automatically controlled, reprogrammable. There have been rapid spread of robots in some industries and in some countries: Germany, Japan, Korea, to some degree United States, but I'll show you actually the US quite notably is a laggard in this. Some industries are very rapid adopters of robots. The automobile industry is at the forefront of this, but electronics, metal products, plastics, and chemicals are also major adopters of robots. Here are just some trends on robots adoption. The orange circles are the average in Europe. There's relatively rapid growth from the early 1990s to the period just before the Great Recession, and then a little bit of a slowdown. The triangles are the US. You can see actually the US is falling behind Europe. That's a topic for another day. It's another thing that I'm working on, but I'm not going to have much time to talk about it, except that some people might ask about this during Q&A, and I'll be happy to answer that then. So what do we know about the impacts of automation or robotics? And there are a lot of studies. Some of them get a lot of playtime on magazines such as The Economist or Newsweek, and they're essentially what I would call feasibility studies. They are based on some sort of back-of-the-envelope engineering calculations of what tasks within what occupations can be automated, project those into the future about what the technology is going to do, and on the basis of this, they reach some conclusions about what fractions of jobs are going to be automated. And there are a lot of things that are wrong with this methodology. A lot of it is guesstimates. But the most important part from an economic point of view that makes this methodology really problematic is that there is nothing mechanical about employment declining because some jobs are being automated. The thing that you're sort of generally interested in economics is what you might call the equilibrium impact of automation or robots, which is that the technology arrives, there's some trade-off about adopting it. There are things that you can do with robots, but you will choose not to do because they're too expensive. Amazon, for example, experimented by using the Kiva robots when they decided a lot of things that they could do with the Kiva robots were too expensive. So they now use them for a limited range of tasks. Others are still performed by humans. And then at the same time, once robots are introduced, that's going to change relative prices, demands, and so on and so forth, and there will be jobs created in other industries and other occupations. And all of those are absent in these sort of feasibility studies. So from an economical point of view, even though they get a lot of attention from the media, they're not particularly informative. So what I'm going to try to do today is, first of all, try to introduce a very bare bones fashion, a framework which I will argue is the right framework for thinking about automation. And then based on that framework, I'm going to show you how you can try to estimate the equilibrium effect of robots, and then I will use data from US local labor markets in order to do that. Okay, so what is the framework? Briefly, what I'm going to call it's a task-based framework. It sort of draws on work that I did with David Otter and earlier work with Pascual Restrepo. It's also related work that Yossi Zeira did earlier on. And I think this is actually, in my opinion anyway, as important as the empirical work that I'm going to present. In particular, I'll highlight what is the crucial building blocks of modeling automation, and why that's sort of different from the usual way that many economists approach technology, and why that difference actually is quite consequential. Be that as it may, I'll come back to that. What I'll also do from this is show you that once you take this framework across space, in particular across different labor markets, there is a relatively simple relationship between the arrival of robots and changes in employment and wages. So in particular, summarizing it, what I'm going to show you that out of this theory, you're going to get two equations of this form. Change in employment, subscript C, meaning in local labor market, or what I'm going to call commuting zone C, as a function of a variable which I'm going to call exposure to robots in that local labor market. And beta E is going to be a parameter you can estimate, and itself is a function of underlying structural parameters in a way that I'll describe. And then you get the same thing with the change in average wages. And the exposure to robots is essentially a very simple object. It links essentially the robot penetration in industry I, which means that technologically what's feasible to do in industry I using robots, which again will make a little bit more sense once I give the theoretical framework, with the baseline shares of that industry. So essentially it's saying how much of the, given the employment distribution across industries, how much of the jobs are actually being threatened by automation, given the technological trends at the industry level. Okay? And then I will follow a strategy similar to what Outer, Dorn, and Hansen, and Bloom, Draka, and Van Rienen, and others have used in terms of trying to exploit the exposure to robots' exogenous characteristics. So in particular, because it might well be that you're seeing this exposure in robots very high in the US in some industries because of some specific things going on in the US. Instead, I'm going to exploit what's going on to this robot penetration in other countries. And that makes particularly a lot of sense in this context because, as I've shown you, the US is a laggard, so they really are following what's going on at the technological frontier in terms of robotization. So this is the plan, and then just to give a little bit away, what we're going to see is that there are a lot of things to discuss. The details are, the devil's certainly in the details, but we're going to see relatively large and well precisely estimated negative effects on employment and wages. Okay? All right. So without further ado, let me jump in a little bit of the technical discussion. So let's think of a world like the US economy that consists of many, many local labor markets. At the end of the day, when we come to the data, I'm going to have 722 commuting zones, which are essentially a collection of little cities and counties that are forming a single labor market. And I'm going to assume that each one of those is indexed by C. Let me first shut off trade between these commuting zones. I'll show you what happens when we have trade. It complicates things a little bit, but nothing major. And the key thing here is that each commuting zone is going to have an output, YC, and then that output is made up of YCI. So YCI would be, for example, car industry in the commuting zone Flint, Detroit. Okay? And then the way you combine them is using a CES aggregator. Sigma is the elasticity of substitution. So you need to do cars, you need to do electronics, you need to do textiles, you need to do restaurants, and so on and so forth. And alpha i's are just some share parameters. The key thing is that, and this is what I mean by the task-based approach, is that production takes place by performing tasks. If you want to do textiles, you need to do spinning, you need to do weaving, you need to do carding, you need to do drawing, you need to do coloring. All of these things together make up what a production process for a particular good is. So XCIS is the performance of task S for industry I performed in commuting zone C. And here I'm going to simplify things, and I'm going to assume that your output is the minimum of what you produce in any of these tasks. So you need to do all of the tasks. If one of them fails or you have a shortfall in one of them, that's going to determine everything. This is just for simplicity for today. The general framework doesn't require this, but this sort of makes it easy for me to tell the story. Okay. So the key thing and the key innovation, and where this sort of approach differs from the ones that are typically used for thinking about technology in the economics literature, is how we model automation or robotization. And that's this equation here. And it says that there are a bunch of tasks, let me call those in industry I to be those above task MI. Those just have to be produced by labor. And labor has some productivity gamma, and then if you allocate some labor, they produce some tasks. But for tasks less than MI, those are automatable tasks. Technologically, we know how to automate them, which means technologically we know how to use machines instead of labor. So RCIS is the quantity of robots used for production. And crucially, because robots are replacing labor within a task, they are perfect substitutes within a task. It doesn't mean that they are perfect substitutes we will see within the entire industry or the economy, but within a task they are perfect substitutes. So that's why this is an addition, and so you either produce robots or you produce labor. Okay. So let's Q denote the price of robots, and W denote the wage in commuting zone C. And a key object here is going to be this red thing, pi C, which is the cost-saving gains from the usage of robots. So if this pi C is equal to 0, it means that at the margin, using one robot versus using one worker costs the same amount. So you're not going to have any cost savings from using robots. If pi is negative, it means using robots is more expensive. You won't use them. But if pi is positive, you're going to use the robots. And how positive it is going to depend on how much your costs go down. Now, this is again a simplification. There are various different things that you can do to generalize this framework. Some of them are important for some other applications. Just to give a heads up on this issue, I think the most important one is that here I'm assuming no comparative advantage. The more general framework has comparative advantage, that people are good at some tasks, robots are good at some other tasks, but for my purposes today, that doesn't really matter. Okay? And then we have some supply curves and market clearing conditions. Let me not say more on that, except this epsilon is going to play the elasticity of supply, or 1 over epsilon, and eta is related to the supply of robots. Okay, so let me, since my purpose is to focus on robots replacing jobs, let me focus on the case in which pi C is positive everywhere, which means if robots become available, in particular, if robots become available in more industries, or in terms of the equation that I introduced here, this MI changes, the extensive margin of automation changes, then firms will be happy to use robots. Now, under those assumptions, you can derive this very simple relationship between labor demand in a commuting zone and the changes in robotics technology. And this is sort of a partial equilibrium relationship, and I'll give you the equilibrium relationship in the next slide, but I think the partial equilibrium relationship is useful to understand what's going on. So in particular, the first term is really the new term, the new sort of conceptual issue here, which this way of approaching robots or the effects of robots makes abundantly clear. And we call this the displacement effect. What is the displacement effect? Well, it is the fact that when robots are cost saving, you're going to use them instead of people. So all else being equal, people are going to be no longer employed in the same tasks as before. And how important is that? Well, it's going to depend on DMI, how much at the margin you're changing the robots, and LCI, which is the share of employment in industry I in commuting zone C. So if you're introducing robots in the car industry, but you don't have any car employees, automobile employees in that particular local labor market, doesn't matter. But if it's happening in Flint, Michigan, it matters a lot. And it's always negative. And this is the important thing that I'm going to emphasize again in a second. there is a first-order negative effect from technological change on labor demand, which is often understated, underappreciated in many macro or labor discussions. But that doesn't mean that technological improvements is necessarily bad for labor, and that's because of the two other terms that are in there. So the blue one we call the price productivity effect, and the green one the scale productivity effect. What is the price productivity effect? Well, imagine we introduce robots in the car industry. What does that do? Well, it makes cars cheaper. Why? Because we assume that pi c is positive, which means there are cost savings. If cars become cheaper, then the car industry expands. If the car industry expands, they want to employ more people because not all tasks are automated yet. So that's the relative prices leading to employment expanding in the car industry. But moreover, if cars become cheap, we're all becoming richer. If we become richer, we don't just want to consume cars, we want to consume more iPhones and textiles and restaurants and entertainment. So there is a scale effect for the economy, and that's the green one, essentially with homothetic preferences, just output. So the change in output. So those two effects are going to together go against the displacement effect. Now let's put all of these together in equilibrium, and you get a similar relationship to the one that I showed you, but now it's the equilibrium relationship, meaning that now I am solving out those price productivity and scale productivity effects themselves as a function of the change in technology at the extensive margin. So everything is now written as part of DMI. The red one is still the displacement effect, and now the blue one is the productivity effect, combining this price productivity and the scale productivity effect. Now, importantly, both for equilibrium wage, which is the second equation, and equilibrium employment, you have the sum of a negative term and a positive term. So this is exactly what I was emphasizing, but now you can see more easily. The negative term is coming from the displacement effect, the positive term is coming from the productivity effect. The other important point, which sort of builds on my discussion, is that the blue term, as you can see, is scaled by pi c. The greater is pi c, the larger is the blue term. Now that's a very important point, because if you read some of the popular press or popular academic discussions of automation and robots, they suggest that the threat to employment comes from these brilliant technologies that are going to replace workers because they are so productive, let alone the fact that we don't see this super high productivity in any of the national income statistics. But leave that aside, the theoretical framework here clarifies that that's sort of backwards. Actually, the real threat to employment comes from not so productive automation, because if automation is very productive, pi c is large, that creates a large productivity effect, and the productivity effect goes against the displacement effect. But the effects on the impact on wages and employment is necessarily negative precisely when pi c is approximately equal to 0, because in that case you're adopting these automation technologies, but they're not super productive, so you're not getting any of the productivity gains. And then these things also depend on elasticities, etc., but let me not go into that. But the other thing that you're seeing here is that these terms all look very similar. They have some LCI here, so oops. They have this LCI here, and they have these S's here, which are shares. But let me now do one more step, and then we're going to arrive to our sort of estimating equation, so to speak. Let me suppose that mi is approximately equal to 0. And essentially what that means is that for the specific technology we have at hand, robotics, at the beginning of our sample, there aren't so many robots. Okay? So under that assumption, you can write these terms, both of these, this term and this term, in a rather simple way, and they're both approximately equal to this thing, which is LCI, which are the baseline employment shares, the times change in the number of robots per employee in that industry, which is exactly the exposure to robots term that I gave you at the beginning. So therefore, under this MI approximately equal approximation, these two equations become very simple to estimate with the data that we have at hand. Okay. Finally, This was greatly simplified because I did not allow commuting zones to trade, but of course that's crazy. You know, Flint, Michigan doesn't produce cars to be consumed in Flint and Detroit, Michigan. They export them all over the United States, so you can incorporate that. The model becomes a little bit more complicated, and the parameters that we estimate become a little bit more complex functions of the underlying parameters, but nothing changes from the point of view of what I've explained. So therefore, with or without trade, this is what we're going to be estimating. Exposure to robots, employment, and exposure to robots on wage. Both of those could be estimated together, but there is no gain, there's no loss in efficiency in estimating them separately, which is what I'm going to do. So I'm going to use data from 722 commuting zones, together with detailed microdata from the census and the American Community Survey and the county business patterns. You can control for very granular data. We'll also look at migration patterns and so on and so forth from the IRS. But the most important element of this data is the robotics data, which comes from the International Federation of Robotics, as I mentioned. And that becomes available from 1993 onwards for a number of countries and number of industries, especially 19 industries at the level of about 2-digit. And we have particularly good data for UK, Denmark, Germany, France, and the Nordic countries. So, as I mentioned, we're going to look at this exposure to robots, but typically I'm going to look at the exogenous component of this exposure to robots, which is for these 9 countries. So it's like US is sort of following them. Just to show you a little bit of the data, here is how it looks like. On the horizontal axis, I have the exposure to robots from these 9 countries, and on the vertical axis, what's going on in the US, and then you can see from the labels of the industries what those industries are. You see the automotive industry is at the very top, the leader, and they're followed by electronics and chemicals and plastics. But the other thing you can see is that all of these observations are below the 45-degree line, reflecting the fact that US is a follower, and also they're pretty strongly correlated, which is the pattern that I'm going to be exploiting. Now, a very important concern, once we go down to it, is going to be whether robotization in an industry is going hand in hand with other technological trends. So this is looking at that at the level of the industry, so you can see which one the industries are. And the first bar there, the sort of the brownish yellowish color, is the increase in the use of robots. So you can see again which are the industries that have the increase in the use of robots. It's pretty much driven by the first 4, automotive, plastics and chemicals, not cereals, metal products, electronics. And you can also see that the other trends, and I'll name what they are in a second, they're very non-correlated with the robotics trends. So in particular, here we focus on the most salient ones. Those include imports from China. During this time period, there has been a huge increase in exports of Chinese manufacturing, low-skill, low-cost manufacturing into the US labor market, and people, including myself, have written about the implications of this. But that's a very separate phenomenon. So that dark blue is, you see, very, very low, and that's not a surprise. I'll show you that in the next figure in a map form also, because essentially the Chinese imports are in the low value-added, low-tech manufacturing, whereas robotization is really a high-tech, heavy industry phenomenon. Same thing with offshoring of parts of the production process to China or other low-income countries. Same thing with the general increase in capital stock or IT capital growth. So they're not very correlated. The only one that's actually correlated among the trends that we look at is increased imports from Mexico, and that's because of the automobile industry. And that's one of the many things we're going to control for, and it doesn't see sort of it doesn't matter for anything, but that is one that seems a little bit correlated. So to show what's going on a little bit more clearly, here is the map of the US with the different commuting zones plotted in there, and a heat map of where the exposure to robots variable is hitting. And you can see the darkest places, which is where the exposure to robots is particularly high, is Midwest This is sort of the heavy industry heartland, the Rust Belt, a little bit in this mid-east area. Whereas if you look at the same type of map, but for Chinese imports, it's a much more of a coastal phenomenon, and you look at the unconditional correlation between these two variables, the spatial correlation, it's essentially zero. So these are very different phenomena, again, as I was emphasizing. The same thing if you look at the location of routine jobs, it's a little bit more correlated, but still quite different than where the robots are. And same thing with offshoring. Now, one thing you would like to know is, this measure of offshoring is telling you where the robots should hit, but it's not based on disaggregated spatial data about where we are seeing the robots being adopted. That data, unfortunately, does not exist anywhere in the world except possibly in France, which we now have access and we're working with the data. It's one of these very funny things is that everybody talks about automation, but nobody's collecting data. So there is no data available on which companies are adopting robots in the United States that you can easily use. So if I were just sticking with the empirical strategy, there will be sort of this lingering question which says, well, you're saying that because of the baseline distribution of employment, you should see much greater use of robots in Detroit because of the car industry, but do we really see more robots in Detroit than, say, Iowa? Well, turns out that there's a very creative paper by two people from Georgia Tech, Nancy Green-Lee and Corey Kraft, which they scraped the web and they got the location of all robot integrators in the United States. And robot integrators are essentially the people who do everything that you need to do with robots. So, robots are not like other machinery. You cannot just buy them, install them, because they need to be programmed and reprogrammed and then maintained. So, except for very few companies like Toyota, which are themselves robot producers, that's outside the capabilities of other companies. So essentially the robot integrators are those that do it, and they need to be located locally. So now, based on the data that these guys collected and nicely shared with us, we have the location of all of the robot integrators. So then we look at what's the relationship between these robot integrators and the exposure to robots. And let me not go through this table yet, because instead I'll go through the same style of table. So let me just show you that in a picture form. And so here is the exposure to robots from 1993 to 2007. I'm going to stop everything at 2007. Not that it matters, but it's cleaner, because otherwise you're getting confounded with the effects of the recession, which are hitting differentially across different regions. At the end of the day, it doesn't sort of matter too much, but that's what I'm going to do. And here I'm looking at the number of integrators. Well, actually, here I'm looking at log of 1 plus the number of integrators, but in the regression, you can do it in whichever way you want. Doesn't really make any difference. And you see that there's actually a very strong relationship between exposure to robots and the number of integrators. And Detroit, that I was mentioning, is at the top there. Now, as in this figure, as in many other figures, you'll see that there are going to be a couple of commuting zones led by Detroit City, Michigan, a couple of others like Saginaw City, Defiance, Ohio, etc., which are quite a bit ahead of the others in terms of their exposure to robots. So everything I'm going to do by including or excluding them, the gray area is the one that includes all of the commuting zones, and the red line there is the one that excludes those outliers. In none of the specifications I'll show you it makes any difference whether you do this sort of exclusion of outliers or not. All right, without further ado, let me come to just the regressions that I sort of announced at the beginning, motivated by the theory. So I'll do them first for employment and then for wages. And they're all going to have the same structure. And the earlier table that I showed you for integrators, I didn't show you, but I went through it, exactly has the same structure also. Here I'm looking in two panels for two different outcome measures in terms of employment. I'm going to focus on the top one, which is private employment to population ratio from the census data, but the bottom panel, which looks from the county business pattern. So the one is counting employment from the employee side, the other one is from the employer side. They give very similar results. So here, this is just the change in employment regressed on change in exposure. Change in employment goes from 1990 to 2007, so more or less around the same time that the exposure to robots measure is beginning. We only have data for 1990 from the 1990 census. We can't use 1993, and it goes to the 2007 American Community Survey, again stopping just before the Great Recession. The first column doesn't have any covariance, so it's not controlling for anything except for census division dummies, so that you're not comparing, the West to the Midwest or anything like that. Okay, so you can see a very precisely estimated, fairly negative effect. What it implies in terms of quantitative magnitudes, I'll come back to in a second, but the quantitative magnitude is not what I want to talk about right now, but it's the fact that it's negative and quite precisely estimated. So what's the next column? The next column starts adding, or the next series of columns start adding successively more and more detailed covariance. So essentially, the first column is change on change, essentially taking the model exactly as it is, but of course the model is leaving out a lot of things that are changing in the composition of the demand or the supply of labor. So in the second column, you control for the baseline demographic characteristics, gender, race, age, educational composition in a very detailed form, so that you're allowing differential trends by these characteristics at the local labor market level. And then the coefficient goes down just a little bit, about 10%, but not much. So this is sort of an important sort of thing to control for, but this comparison shows whether you do or do not doesn't really matter. The third column is even more important, perhaps. It controls for broad industry shares. Where are robots being adopted? Where you have manufacturing. We don't have robots in healthcare or education at the moment. So it might well be that we might be inadvertently capturing differential trends by places that have manufacturing versus those that don't. So here what we do is we control for baseline share of overall manufacturing, durable manufacturing, services, and construction industry. So remarkably little difference from column 2. These changes are not what's going on. And in the fourth column here, we control for all of these other competing trends at the industry level, again, projected to the commuting zone level that I showed you on the sort of in terms of the maps and the bar charts a second ago. Penetration of Chinese imports, Mexican imports, offshoring, routine, and so on and so forth. Remarkably, again, the coefficient doesn't even budge. These specifications are weighted by population. If you do unweighted, it doesn't matter. And then the final thing, outliers are not important. Whether you exclude those outlying areas or you do other procedures in order to downweight outliers, it doesn't make much difference, which are columns 6 and 7. Diagrammatically, this is how the data looks like. This is the specification that controls to the most loaded one in column form that I showed you with all of the competing controls and so on and so forth. You see again a very well identified, very precisely estimated negative relationship. You see again, you see again these places like Detroit City, Wilmington, Defiance, and so on and so forth. If you exclude them, instead of the black line, you get the red line. Not much of a difference, as you could see from the numbers a second ago. Same thing for wages. So here you see the wage regressions, again, fairly stable. Now you're using the microdata. It doesn't really make much difference whether you use average and do it or you do the microdata, but since the quantitative magnitudes I'm going to come back to, let me just show you this in a figure form. You see the very precise relationship between exposure to robots and what's going on with wages. Again, you can see the commuting zones that are at the forefront of robotization, but whether they are or are not included is not very important. So these are the basic patterns. What I'm going to do next in the remaining 15 minutes, first give you a little bit of a sense of what the quantitative magnitude implies, and then I'll go through a series of concerns about whether this is really capturing what we say is capturing, or it's some other confounding effects going on that we really have everything backwards. So I'll try to reassure you that that's not the case. And then I'll show you finally the heterogeneous effects. What's the effects on men versus women, older, younger, educated, uneducated workers, and so on and so forth. All right, so to go to the quantitative effects, we first need to turn these into IV. Let me not spell that out. Works out pretty straightforwardly. Let me just jump right away to the quantitative magnitudes. And these quantitative magnitudes are large, but I would say not implausibly large, and nowhere as large as what would be the basis of end of work type of arguments. And there are two ways of reading the quantitative magnitudes. One is pretty safe, which is to say these are local estimates. I'm comparing across different commuting zones, and let me interpret them as local estimates. So in particular, you can say, what's the effect of one more robot, say per 1,000 workers, so that it's normalized, one more robot per 1,000 workers. By the way, it's sort of, if you look at what's the penetration of additional robots in the US economy, it's about 1 per 1,000 workers over the 1993 to 2007. So that's a good number to bear in mind. So one more robots per 1,000 workers. What's the effects of that in a place like Detroit versus a place like Oregon, which doesn't have much exposure to robots? And the answer is that it reduces employment by 1/3 of a percentage point, employment to population ratio. So that's a large effect on the one hand, but it's a small effect on the other hand. If you look at the overall decline in manufacturing employment, it's about 10 times of this during this time period. And it also has non-trivial effects on wages. It leads to about 0.75% slower growth of real wages. Now, these are local effects, and if you want to translate from local effects to aggregate effects, you need to make some assumptions. So in the baseline model in which there is no trade, those baseline assumptions are made for you, because they say whatever is happening to a commuting zone, you can just sort of aggregate it up. So if you do that, you're going to get the same numbers for the US economy. So you're going to get 1/3 of a percentage point, just slightly more than a 1/3 of a percentage point, lower employment to population ratio. Again, not trivial, but not a huge number relative to what's going on in the US economy, and about 0.75%, 0.73 percentage point, slower wage growth. But that's not reasonable because, obviously the productivity effects that I went through are not just local, but they're going to be spreading throughout the US economy. So really the non-robot places like Oregon are indirectly benefiting from the automation that goes on in other parts of the economy. So if you incorporate that using the trade model that I did not present, so therefore I won't go through the details, somewhat surprisingly, but we can talk about that in the Q&A why that's going on, you essentially end up with some attenuation of these effects, but not a big one. So this one goes from 0.37 to 0.32, and the wage effects are attenuated a little bit more. They go from 0.75% to 0.5%. Okay? So I'll come back to these at the very end if I have time. But let me sort of do a little bit to reassure you that these are not capturing other changes that were already ongoing in the US labor market. So in particular, the first concern you might have in this regard is that places like Detroit or Defiance City were already declining before the robots arrived, and the fact that they adopted the robots is a consequence of that decline, or is part of that decline. Now, we are partially insured against that because we're using the changes in the technological frontier as approximated by the European countries here, but it might still well be that they were in a decline. So one easy way of checking that is to do exactly the same exercise, but on the left-hand side, include employment and wage changes in the prior 2 decades. Rather than look at the 20 years or so after the beginning of the robotization, look at before. Since the robots were not around before, not much robotization going on before the 1990s, there should be no relationship, and in fact that's exactly what you find. This is employment, this is wages, not much going on. So this is reassuring, but it's not enough. And one of the reasons it's not enough is that perhaps there is some other special things going on. Perhaps everything is being driven by autos, and there might have been, the auto industry was doing okay in the 70s, in the 60s, but it started having problems in the 1980s. Perhaps that's what we're capturing. So, so we do that by looking at sort of the auto industry separately, and that doesn't change anything with or without autos, and the autos by themselves have very similar effects. That's a little surprising, actually. I would have expected at least the robots in the auto industry perhaps to be different from the electronics industry, but if you look at the numbers, they're actually quite similar. We also look at allowing for linear trends so that you're really exploiting what's going on within a commuting zone over different periods of time. That doesn't change anything. But one other concern I want to sort of briefly talk about is that perhaps what might be going on is that at the same time as you are adopting robots, you're making other changes, and then we're confounding those changes at the industry level with the introduction of robots. Again, the first sort of set of bar charts that I showed you suggested that might not be so important because many of the important trends were somewhat different across industries. But we look at that a little bit more carefully here. And in particular, here we are looking at the same sort of strategy, but controlling for overall changes in the capital intensity and the use of personal computers. And what's nice here is that you can see that it has no effect, these controls themselves have no effect on, on the effects of robots, which remain essentially unchanged and negative, precisely estimated both for employment and wages. But also interestingly, the effects of overall capital and computers themselves are very different. And that goes back to the conceptual framework that I started at the beginning. What I emphasized, because that's where I was building up to, was the impact of automation. But you know, there was the parameter gamma there, which increased the productivity of labor. What's the effect of increasing the productivity of labor, leaving everything else constant? You can go and check, and you'll see that it's quite different from the effects of automation. While automation creates this displacement effect, increasing the productivity of labor, like a standard labor augmenting technological change, doesn't do any of that, and it shouldn't have any of this negative impact. And that's essentially what you're seeing here. If you increase the capital intensity, or sort of perhaps invest in other types of technologies, you have a slightly positive effect on employment and a somewhat precise and larger effect on wages. And even computers, which are mixing both this augmenting type of technology together with some type of replacement, because if you think of computers, you know, they're inherently linked, intimately linked to things like the numerically controlled and the computer-assisted machinery that was already spreading in the 1980s. You see not much of a negative effect on employment, a little bit of a negative effect on wages. But this sort of emphasizes that the specific type of technology and the extent to which it's creating this displacement and productivity effects is going to vary, and it's very important to sort of take that into account. All right, finally, in the last 5 minutes, just before I conclude, let's look at the heterogeneous effects of it. So the first thing you might wonder, not worry, this is not, the worries we've left behind, so now we're coming to wonder, the effects on gender. Is this affecting just men? And the answer is, well, not really. I mean, it has a negative effect both on men and women, but the effects on men is a little larger, which might be sensible because the workers that are being directly displaced are the men. More interesting, perhaps, are where do you see these effects? So the microdata nature of the census files enables us to be very granular about looking at which type of occupations, which type of industries are being affected. So here, what I'm showing you is the estimates in a simple bar chart form, together with their confidence intervals around it. I'm doing that from 3 different specifications, but you know, doesn't matter which one you use for most of them, and I'm doing it for a number of different industry groupings. You can do it in a more granular level, but it's harder to present, so I have just opted for this way of presenting. So there are two things that I would like you to take away from this chart. The first one is that the effects are concentrated exactly where you should expect them. So you see that it's the highly robotized manufacturing industries where you're seeing the decline in employment. And you're not seeing any decline in employment in other manufacturing industries. If this were reversed, that would be very worrying, because we're saying this is going on because of displacement, but you're not seeing the effects where they should be, you're seeing them somewhere else. But also interestingly, you're seeing spillover effects not on manufacturing, but on services that support manufacturing. So in particular, you're seeing it in services in retail and business services. And so that's actually quite consistent with sort of the qualitative evidence that you see from these small towns that were focused in manufacturing. A major factory closes, and then that creates a depressed labor market, and then other shops start closing, and that's, you're seeing a version of that. Same things at the level of the occupation. The effects is concentrated on blue-collar workers, assembly workers, mechanics, but there's a little bit of a negative effect on clericals and a little bit of negative effects depending on specification on professionals. But the other thing that you might sort of care about is, you know, are robots affecting just one specific type of education or skill group? And the answer is yes and no. So here we're looking at the employment, and here we're looking at the wage effects by education groups. And you see that most of the negative effects fall on middle skill workers, but, oops, where did we go? But there's certainly an effect on the lower skill workers also, and not much on the higher skill workers. Now, ex ante, I would have perhaps even expected people with postgraduate degrees to get a wage gain, but at the end of the day, we're not seeing this degree of complementarity between automation and even the more skilled workers. A different way of looking at this data is not by education group, but the wage percentile. So this estimates the entire wage distribution, or the effects of the robots on the entire wage distribution. And the story is sort of similar. There is a negative effect at the lower end, all the way up to about 60th percentile of the wage distribution, and not as positive or not a negative effect at the top. All right. So let me just end with two more things. The first one is, I talked about the quantitative magnitude, but when we looked at the effects by industry, we saw that some of what we are capturing are these negative spillovers onto supporting service industries. Now, that raises a question as to when you aggregate this up, whether you should include that or not. Because that might just be a local effect that has no similar component at the aggregate level. So one way of doing that is to redo the numbers, excluding those spillovers, and when you do that, you end up even with a smaller number, 0.2 percentage points declines in employment. So my best case would be that the negative aggregate effects would be somewhere between 0.2 and 0.35, or somewhere around that. So it's a negative effect. It's a very precisely estimated negative effect, but nowhere at the level to support the sort of concerns about end of work. But on the other hand, to conclude, it also very clearly underscores that the view that, oh, you know, technology always is the tide that lifts all boats, we have nothing to worry about, is extremely misplaced. The way of thinking of technology as a black box, it will just increase productivity and that productivity will spread, I think makes little sense in general, but it makes particularly no sense in the context of automation technologies, and the automation technologies in particular, to the extent that they are replacing tasks previously performed by labor, they will clearly create this displacement effect. That displacement effect may be counteracted by the productivity effect. My previous work with Pasquale was also emphasizing that it may be counteracted, and in fact, historically, it has generally been counteracted by the creation of new tasks in which labor has a comparative advantage. So there's a dynamic endogenous technology element to this, which, you know, at this frame, both time frame and empirical frame, we did not address. But all of those are important ideas to bring to the table, but certainly they do not support the complacency of, oh, this time is going to be no different, therefore we should not worry about the implications of technologies. I think there are very important questions to be asked about what are the implications of technologies going to be, how can we actually make sure that we create the complementary skills so that the positive effects outweigh the negative effects and so on. So let me stop at this point and take questions. Thank you.